welcome you all joining us either online or here at the Wisconsin Energy Institute. This is your first time joining us for one of our programs. My name is Scott Williams. I'm the Research and Education Coordinator here at the Wisconsin Energy Institute. And the Sustainable Energy Seminar Series is an event that we hold every other week here in the fall and the spring semesters to highlight the cutting edge energy research from across UW-Madison and beyond, and to showcase how different disciplines understand energy challenges and develop solutions. And throughout the series, we hear from experts in science and engineering, as well as social sciences and humanities, to learn about the ways in which they view sustainable energy challenges and solutions. The seminar is open to the public and is also a course for students in the undergraduate certificate in engineering for energy sustainability, as well as the master's in sustainable systems engineering. The seminar is presented in a hybrid format, and we always welcome you to join us here at the Wisconsin Energy Institute in person, but you're also welcome to join us via Zoom as well. If you are joining us online, live captioning is available. You can hit the show captions in Zoom to turn on that feature. If you do have a question for a presenter, you can use the Q&A box, and Professor Anderson says he's willing to stop partway if you have a question you need clarification on during the presentation, so don't hesitate to use the Q&A box. Or if you're in the room here, feel free to raise your hand.
Shout really loud.
With that, I'll introduce our speaker today. Mark Anderson is an associate professor of mechanical engineering, and he directs the Thermal Hydraulics Laboratory here at UW-Madison, which is focused on experimental aspects of thermal energy transport across several different energy sectors, including advanced nuclear, storage, waste heat recovery, thermal energy storage, and advanced power cycle development. Professor Anderson studies the physics, thermal hydraulic performance, and material corrosion issues of several different fluids, including salts, liquid metals, supercritical water, and supercritical CO2. And he'll be talking today about advanced energy utilization through advanced power cycles and thermal energy storage. Welcome.
All right, thank you very much, Scott. All right, so yeah, I'm going to talk a little bit about improving energy utilization. So I'm going to start with this slide. I don't know if you guys have seen this from some of the other talks. This is a slide that's put out by Lawrence Livermore National Laboratory, but it kind of tracks the U.S. energy consumption from different sources. So what it does is it shows all the different sources over on this side, and then how that gets to the customer. And a couple things to note. One is the numbers that are here are in quads. A quad is defined here as a Quildren BTU. And these are some of the approximate values of one quad. So for instance, 9 billion gallons of gasoline is one quad, right? So if we come here and we say that we're producing 13.3 quads of electrical energy, that's up on this spot here, then you can look at how much gas that would make to generate that, right? So I wanted to look a little bit closer at this and look at these different sources. So here you have coal, natural gas, geothermal, and I kind of put a box around each one where we have thermal energy. So most of our electrical energy is generated from thermal energy first. We generate thermal energy, and then we convert that thermal energy over into electrical energy. So if you look at all these boxes, these feed into this electrical generation box. And most of that comes from hot heat sources. So natural gas, geothermal, coal, some nuclear, some CSP or concentrated solar power. And only a little bit is not generated by thermal energy. So this means that we have to look at these power cycles and how we create the electrical energy from these thermal sources, right? So this slide just breaks it down a little bit and talks about the sources and so forth. I have a couple little QR codes on the presentation. So there's a bunch of slides and I pull some information from the web and so forth. So if you're going through this and you want to know more information about a particular slide that I pulled from the web or something, I have a QR code so you can go to that directly. So if you go to this, you go to the Energy Information Agency, which is the U.S. Energy Information Agency, and then it will bring up this particular site. So what I'm going to talk about today is how we improve energy utilization. And this is kind of a picture of a bunch of different sources. So these are high temperature heat sources. This is thermal energy storage. And then we somehow have to make the electricity with some kind of power cycle. And I'm going to specifically talk about supercritical CO2 power cycle as we move along. But then you can also do some waste heat recovery and feed that back in. So there's many different components to this. I'm going to touch a little bit on supercritical CO2 cycles and a little bit on thermal storage if we have time. So we'll first focus on the supercritical CO2 cycle and how we produce that electrical energy from this heat energy. So this could come from solar thermal, it could come from nuclear reactors, it could come from fossil or any other kind of heat source, geothermal. So before we get into the supercritical CO2 cycle, I want to talk a little bit about basic thermodynamics. So we'll do a quick little review. So we're going to create electrical energy from thermal energy. So to do that, we need an engine, essentially. So we need some high temperature heat source. We need some low temperature heat source. We have to reject some energy to this low temperature resource, and then we can produce some work out, right? So this is basic thermodynamics. If you look at the first law and second law of balance with regard to the first law, or with regard to thermodynamics, we look at entropy and energy generation, then we can come up with the fact that there's certain cycles that can reach 100% efficiency. Or there's certain cycles that limit the amount of energy that you can get from it, the amount of work that you can get. So one is the Carnot cycle, and this gives the definition of the Carnot cycle. So this is a theoretically perfect cycle. So if I built a perfect engine, I could only get an efficiency that's associated with this particular equation, which says we have 1 minus Tc over T hot. So the colder this temperature is and the hotter this temperature is, the higher my efficiency can be, right? And if you look at the Carnot cycle, it looks like this on a TS diagram. This is temperature entropy. And we have an isothermal process here and an isothermous process here. That just means that we're adding heat at constant temperature and we're rejecting heat at constant temperature. So if we wanted to do this in a practical situation, we could look at using water in the vapor dome. So this is the vapor dome. And inside of the vapor dome, as you move from point 1 to 2.2, you're at a constant temperature, right? So you're moving across here. So I can put that Carnot cycle essentially inside of a vapor dome of water. And historically, that's what was happening, is we were looking at trying to create electrical energy from heat. And it turned out that water was a good working fluid. It's very available. And we can stick this thing, the Carnot cycle, inside of the vapor dome, and we can realize the Carnot cycle to try to get the highest efficiency possible. Before we go too much further, I want to talk a little bit about power versus efficiency and power versus heat. So we said that we have a heat engine here. And in order to drive the heat from the high temperature source to the engine, and then from this to here, we have to have a temperature difference. So we could have two situations. Say we take this cycle and we have a hot temperature, we're producing heat at this particular point, and we're running our cycle here, and we're rejecting at this point. This gives us essentially zero power because I have no temperature difference between the engine and the heat source. So I have no heat transfer associated with that. If I want more power, then I have to increase that temperature much higher than the working fluid to drive heat transfer. And this is going to give me a rate of heat transfer, and then I can get more power out, right? So I could get the same amount of energy from these two, but I can't get the same amount of power. So there's a trade-off with that. So if I want to get power, and that's what we want, we don't care if we have energy, we want the lights to turn on now versus be really dim for a very long time, right? So we have to have a little bit higher temperature that drives that heat transfer process. So keep that in mind as we go forward, that we're interested in power and not just energy. And that requires higher temperatures. So it turns out that this Rankine cycle, this ideal Rankine cycle that was inside of this vapor dome, we have to modify it a little bit to make it practical. For one instance, you don't want to put wet steam through a turbine because that can damage the blades. A turbine is a fast spinning object, and if we have water droplets impinging on it, that can wreck it. So then we go to superheated steam, and then we expand outside of this vapor dome. So we do that for practical reasons. And then it turns out that it's very hard to pump a two-phase fluid too, right? So we can't go straight up in the vapor dome because we're a two-phase liquid. So we bring this all the way over to this side where we're liquid, and then we can pump that liquid up, and we can do that much more efficiently. So we're essentially taking the Carnot cycle and we're saying, okay, yeah, we like the Carnot cycle, it's very efficient, but we need to have a practical running system. So we're modifying it a little bit. And now over the years, so this is how we've produced electrical energy for a very long time, so over 100 years, we've made significant improvements on this. So we've gone from a very simple cycle, we've added some reheat where we're heating this up again. We've added some regeneration associated with this. So we do reheat and we try to recuperate some of the heat within the cycle. And by doing that, we can drive the efficiency up. So there's a trade-off between adding these different components and increasing the efficiency of the cycle. So all of that comes at a price. So yeah, there's always a trade-off associated with that. So I have to add all these different turbines. I have to add these feed water heaters, but then I realize a higher efficiency. So this one probably gives me a 25% efficiency. And then if I do all these modifications, I can push that cycle up to 35% efficiency. But it comes at an expense, both complexity and cost of components. And so if you look at a real power plant, it looks something like this. So it deviates significantly from those simple diagrams that we had. And we have a bunch of these different feed water heaters. These are just internal heat transfer in the loop. We have a bunch of different things. There's a high pressure, low pressure, double stage low pressure, and they get quite complicated. And the purpose of that was to increase the efficiency because we want to have as efficient a process as possible. So there's this trade-off between cost, efficiency, and simplicity and complexity. Now, other cycles, so about 43% of electrical generation is from combustion of natural gas. This occurs at fairly high temperatures, about 1,000 to 1,200 degrees C. If we look at steam, the steam pressure as a function of temperature goes up like this. And so if we're at 1,000 degrees C, we're at very, very high pressures. And so that's a problem with some of these steam cycles. So if we want to make use of this high temperature heat, there's another cycle called the Brayton cycle. And this is an open gas Brayton cycle that we can look at. And the idea here is that we send in our natural gas, we take in some air, we compress it, mix that air with the natural gas, we combust it, and then we can take that combusted gas and goes in a turbine. This is the same kind of cycle that happens on your 747 as you're flying. They use jet fuel, but you can do the same thing with natural gas. Unfortunately, that even though we're at this high temperature of 1,000 to 1,200 degrees C, 1,200 degrees C, our efficiency is pretty low. The big problem is that we're trying to suck this air up, compress this air to a high pressure, about 7 MPa, and bring it into this cycle. That costs a lot of work. So we produce power in the turbine, but we have to drive the compressor. And so that's called the back work ratio. So we put in a lot of work to drive the flow up there, and we result in an efficiency of only about 20%. So even though we're at this very high temperature, the cycle isn't very efficient, right? Now we can take this cycle and we can do the same thing we did with the Rankine cycle. We can improve upon it by adding all kinds of different things. Here we add a recuperator. So we try to capture some of the waste heat. We do the combustion process, goes through the turbine, then we take the exhaust gas, come out and try to use that to heat up some of the air that's going in. We can also do reheat and try to improve the cycle a little bit, but we really can't push the efficiency up very high. So what has been done, and this is kind of the state of art of producing power in the United States right now, is the combined cycle. So the idea here is we take both cycles. We take the open air gas Brayton cycle, and we take the steam Rankine cycle, and we put this on top and this on bottom. And we take the waste heat that comes off of the turbine from the Brayton cycle, we feed that into the Rankine cycle, and we can produce steam. And so then we have a system diagram that looks like this. We get about 26% efficiency from the gas cycle. We get about 40% efficiency from the steam cycle, and we get a combined efficiency of about 50%, 48%. So this is the current technology that's out there. This is the best they do. If you go to Walnut Street, you'll see a combined cycle plant. If you go to any large natural gas plant, you'll see a combined cycle because we get this high efficiency. One of the issues is that this only works with burning fossil fuels or fuels, right? So we're using an open air Brayton cycle here. We're ejecting the gas out. And so we're producing CO2. And so we want to look at, as we start to raise the temperature of different processes, so say we want to build a sodium fast reactor that's operating at 550 degrees C, a molten salt reactor that's 750 degrees C, a gas fast reactor 750 degrees C, or a concentrated solar power plant that's at 750 degrees C. How can we utilize these cycles in this system where we're producing no CO2 emissions? So each of these different technologies are zero CO2 emission, and they're higher temperatures, but we have no gas flowing through there. One thing to point out is that as we go to these high temperatures, we have some materials issues. So this is a picture of some steel that's at 750 C. So you can see it's glowing orange color, and there can be, the strength of that material gets much less. So you could imagine bending a bar of steel that's at this temperature where you couldn't at if it was at room temperature. So the strength of the materials go down as a function of temperature. And you can
sorry, wanted
to.
Yep. Your point about the combined cycle for natural gas, those are typically just, I just want to emphasize, that's typically for like the larger natural gas plants that run more often, whereas there's also the kind of the peaker plants that are just use the combustion turbine, right?
Yes, that's true. Yeah, so if you go to Walnut Street, they're operating that all the time. If for some instance you're driving most of your electricity from PV or something like that, and a cloud comes over and you have to kick up power really quickly, then you either kick on like a diesel generator or a natural gas generator where you're just burning that fuel, and you're not getting this efficiency. So you're only getting that 20% efficiency at that particular point. Yeah, that's a good point. Thank you. So as we go up in temperature, what we see from this is that the strength of the material drops off as we go to high temperatures. So this is a concern. So this is something we have to consider. So we want to drive to high temperatures to get higher efficiencies, but we're also fighting some of these materials, right? So we have to, so as if we take this particular one, as you're moving along, this has a allowable strength of, this is in PSI stress. As we move along here, it drops off significantly as a function of temperature. And then we can go to higher temperature alloys, but then the cost goes up. So if we look at like this one up here, this is a nickel cobalt alloy. That's significantly more expensive than regular steel. So there's ways to get to the higher temperatures with these different materials, but it costs money, right? So again, there's a trade-off between, okay, I want that high efficiency, but it's going to cost me because I'm going to have to use these more expensive materials as I drive up that temperature. Okay, so we can start to look at advanced power cycles. And one way to do that is to look at supercritical fluids. And supercritical fluids are fluids like water, but they're operating above this vapor dome. So we were first operating inside this vapor dome. We threw our little Carnot cycle in here. Well, now what we're going to do is we're going to push the cycle up to higher pressures and higher temperatures. We look at water, this looks good, except that the pressure goes up significantly with water. So as I go up in temperature, not only does the temperature increase, but the pressure increases. And since we have this problem with these materials, as I go higher in temperature, then I lose strength in materials. I can't hold that pressure back. So I would need very thick walls. It turns out that if at carbon dioxide, we have a very similar system. So this is the vapor diagram, the TS diagram of carbon dioxide. And if we look at this, this is the supercritical region of carbon dioxide. And it looks very similar to water. The only difference is this is at much lower temperatures and much lower pressures. So the idea is that we might be able to use supercritical CO2 as a working fluid. One other advantage of the critical point is that we get a spike in the specific heat. So this is the specific heat of the fluid, and this is essentially the amount of energy the fluid can hold at a specific temperature. Right near the critical point, the specific heat spikes theoretically to infinite. So you can hold a lot of energy in there at that particular temperature. So this becomes a very power-dense fluid that we can deal with. And then we get slight changes in the density. And it turns out that for the supercritical fluids, I can be like a gas up at high temperatures, and I can be at like a liquid density at low temperatures. And that will become important as we go through this in a second. So we're going to look at the CO2 cycle, and this is now a closed CO2 Brayton cycle. So we're no longer ejecting anything out. It's a completely closed cycle. And it turns out that if I go to temperatures above about 550 C, CO2 cycle starts to get much better than even the combined cycles. So I can get to efficiencies of 50% or so with these CO2 cycles. Another advantage is the size. The power density associated with these CO2 cycles is quite a bit smaller. So for a 10 megawatt system, this would be a steam system. This would be a supercritical CO2 system. So it requires a lot less materials. Now I don't have to have as many materials to build the cycle. It can be smaller, it can load follow better, all kinds of advantages associated with that. This again just shows size differences. So this is the size of a 250 megawatt steam system. This is a helium Brayton cycle, and then this is a supercritical CO2 cycle. So the power density of this supercritical CO2 fluid is very, very high because of this spike in the CO2 and the specific heat. And so this is an image of a compressor wheel for supercritical CO2 at 50 kilowatts, and the thing's just the size of a quarter. This was one that was done at Sandia National Labs. So again, there's a QR code here if you want to learn more information on that. So this is what the cycle looks like. So we're going to operate above the vapor dome. So this is the vapor dome, and we're going to operate the cycle above that. And so we're going to add heat here. We're going to go through our turbine up like a gas, but then we're going to compress it down here as like a liquid. And then we get rid of this high pumping costs associated with compressing it. So it essentially combines the benefits of both the Rankine cycle and the Brayton cycle. We have high power density like a Brayton cycle. We have fewer and lighter components like the Brayton cycle. But we have significantly reduced pumping power like the Rankine cycle. And we're a closed system like the Rankine cycle, so there's no CO2 emissions coming out, assuming that we use like nuclear heat or CSP or something like that. So we'll just walk through this cycle a little bit. And so if we look at the operating conditions of a CO2 cycle versus a Rankine cycle, the Rankine cycle is operating down here. This is the specific volume. So high specific volume means low density. So this is low density. That essentially corresponds to low power density. Here we're further this way, which means that we're low specific heat, or low specific volume, which means high density. And so we're higher density, and we're at much higher temperatures across our turbines. So we're getting higher efficiency associated with that. So then if we look at the different components, we have a main compressor here. This main compressor is operating very near the vapor dome, and on the left side of the vapor dome, where this is primarily a liquid. So the density is on the order of water. So it's about 800 kilograms per meter cubed, and we can compress this very easily. So it's not like a gas. So we had a problem with the Brayton cycle because we were trying to compress air. That takes a lot of energy. It's a lot easier to pump or compress a higher density fluid. And so we can compress that fluid here. So that helps our efficiency. So what that does is it lowers what's called the back work ratio. And then what we're going to do is we're going to come through here and we're going to go through a recuperator. And so we've gotten some heat from the compressor because this costs some energy. So we're putting in energy. We heat up a little bit. We get some heat associated with that, but then we're going to go through here. And in a minute, we'll see that we're going to send hot gas through here, and we're going to recuperate some of that heat from the rejected gas that comes out. So this is just a heat exchanger. Typically, these are compact heat exchangers, so we're making use of advanced manufacturing techniques, which I'll talk about in a minute. Then the next step is from 3 to 4. So we go in, this is where we add our primary heat. So this would be heat coming from your nuclear reactor, your CSP plant, or something like that. We add the heat there, and then we go across the turbine from 4 to 5. So we spin across there. This is where we get our power out. So this is hooked to a generator, and this is producing our electrical energy. And now we have to eject some of the gas that comes out. And so we're rejecting it at pretty high temperature, but we're going to make use of this. So we're going to put that back into this heat exchanger, and we're driving heat from here into the fluid that was coming this way, right? So we're not getting rid of this heat, we're using this heat. So we're using this heat internal to the cycle. And the only heat that we reject is from 6 to 1. Now, if we look back at our heat engine, we know we have to reject some heat. That's just the way they work. You add heat on the hot side, you reject it at the cold side, and we're just rejecting from 6 to 1 here. So we're trying to minimize the amount of heat that we're rejecting. The more recuperators we put in, the lower we can drive this, but then you start adding more components too, right? Another advantage of that heat rejection is that if you look at the difference between a steam Rankine cycle, this would be your constant temperature of steam, and you'd have to reject the ambient. So say ambient's here, this is your temperature, you have to drive it across this delta T. So typically these Rankine cycles, they like to have wet cooling. So that's where you see these big cooling towers, or the Rankine power plants are next to a river or on a lake or something like that. It's because this delta T is very small. So with the CO2 cycle, we're rejecting heat from 6 to 1 here. So that allows us to do air cooling. This is advantageous because we don't have to be located right next to a river. We don't have to have the cooling towers, and we get rid of a lot of issues associated with it. We lose a little bit of energy associated with that because we're at a larger delta T, but we make up due to the fact that we don't need these cooling towers, ponds, rivers, so forth. And we're not putting heat into those. So if we look at these different systems, so a very complex Rankine cycle, maybe you get a 40% efficiency. For a very, very simple CO2 Brayton cycle, you can get 45% efficiency. So we're gaining significantly in terms of the efficiency of the plant operation by going to these supercritical advanced cycles. And then we can further optimize these. So this is a very simple cycle. We can add more recuperators in. I mentioned this a little bit. So the more recuperators we add in, the more heat the less heat we reject. And then we can do recompression and so forth. So we can make these more complicated just the way we did with the Rankine cycles, and we can drive up the efficiency. So we can go from 45% efficient from a very simple system to 50% efficiency as we start to modify and enhance these different cycles. So what does this mean, or why is this possible? One is enabling technologies. So we mentioned that we need these recuperators to capture some of the heat within the cycle. So it turns out that the advanced manufacturing to create very small micro channels and very compact heat exchangers has enabled this to become reasonable. So now I can build these heat exchangers that aren't super massive, that can be pretty small, by the fact that I can use additive manufacturing, or I can use advanced manufacturing techniques to create these high-tech heat exchangers. Also, the turbo machines on these things are quite a bit smaller, and they require higher accuracy and higher tolerances. So when they were building the steam Rankine plants, they didn't have the tolerances. They couldn't machine to those tolerances, but nowadays we can. So we can do much better machines at smaller sizes. So advanced manufacturing in terms of machining tolerances and so forth has added to that. And then as we're going up to higher temperatures, we can look at advanced materials. So we look at these nickel and cobalt systems and so forth. And because the systems are quite a bit smaller, we don't take a huge hit on the costs associated with it. Because the turbines are small, we can use very high temperature alloys within there. Whereas if we were doing a steam turbine, the cost would just be astronomical. And then also improved bearings allows us to get to higher speeds. So we can spin some of these machines up to 60,000 RPM and get higher efficiencies as we go to higher speeds. But that requires some advances in some of these bearing technologies. So this turns out to be a cross-cutting effort over several different power sources. So we talked a little bit about advanced nuclear systems, so the sodium fast reactor, gas fast reactor, molten salt reactor. So this is a perfect cycle for all of those cycles that are operating at the 750 degrees C. We showed that the CO2 cycle becomes much more efficient than the Rankine cycle above 550 C. At 750 C, we're several tens of points above a Rankine type cycle. We can also make use of this for fossil energy, and I'll talk a little bit more about this in the next slide. But we can run what's called an oxy-combustion cycle. And we can actually burn fossil fuels, but we can capture any waste associated with that fossil fuel. And I'll talk about that in a minute. We can use this for advanced high temperature CSP generation. So CSP generation essentially has a bunch of mirrors that shine up a big tower. They heat up a molten salt or oil or something to high temperatures. And then you can take that heat and you can bring that into the working fluid CO2, and you can run your power cycle off of that. So we can use that. It also turns out that we can make use of some waste heat that we hadn't been before. So steam Rankine cycles are huge beasts. It's hard to incorporate all the components and so forth. These CO2 cycles are quite compact and they're easy to put in some location where you have waste heat. So if I have like a natural gas compressor or something like that, I can put a supercritical CO2 cycle next to it, and I can take the waste heat from the natural gas compressor and I can turn that into electricity and then power the compressor, right? So we can reduce the amount of energy that we're using by capturing some of that waste heat. And the fact that this is a compact size system, simple to integrate and so forth, makes that possible. I wanted to say a little bit about this oxy-combustion cycle. So it turns out that, say we still want to burn natural gas, but we want to use a supercritical CO2 cycle. We can send our natural gas in here. We can compress some air, and then we have to separate the oxygen out of the air. So we separate that there. Now we have natural gas and oxygen. We come in, we can burn that. But then we take the waste stream product, which is primarily CO2, and we can bring that into a system, condense the CO2, and then we can put that into a pipeline, and we can use that for chemicals and so forth. So we could put it in your soda, or you could put it in some other kind of chemical process. So we essentially capture any CO2 before it goes out the stack into the cycle, and we run that supercritical CO2 Brayton cycle around by capturing the CO2 in the system. So that allows us to burn the natural gas, but limit the amount of CO2 that you're putting into the atmosphere. Oops, I forgot we had this. So overall, there's a bunch of different advantages of the supercritical CO2 power cycle. We have higher cycle efficiency, lower operating costs, lower capital costs, potential for different heat sources. We have decreased maintenance because we have less systems associated with it. Lower water usage. We talked about using air cooling versus water cooling. These systems are quite a bit smaller, so we can start looking at load following. One of the issues with these big steam plants is that to capture a load event where there's a high load that comes on, or you have a PV plant that drops off suddenly or something like that, and we have to ramp up a system, the fact that these things are much smaller, we can speed these up quicker and get power out. Whereas a steam Rankine cycle, they like to operate at a continuous temperature. If you bring them up too fast, you can get thermal stresses in there and crack them and so forth. So you have to be careful with steam systems. These things are much smaller and you can get improved load following, high power density, and then ultimately lower operating costs and maintenance costs. So there are some examples of this. So a company called EcoGen Power Systems, they've built a couple of these skids that are hooked up to waste heat recovery. So they connect these to natural gas pumping stations and they can produce electricity. So they've shown that this works quite well. And then I put two other examples. I think Scott sent these out. Maybe you did some reading ahead of time. But you can go to this site, 10 megawatt SCO2 demonstration site. So there's some work going on right now at Southwest Research Institute down in Texas where they're doing a demonstration of a 10 megawatt system. So this is actually coming online this year. It's been working for the past 5 years, but we're just about to the point where we can spin this thing up. And the idea is to prove out this technology. So we have all the turbines, we have all the heat exchangers, the whole system's together, and we're going to test this at 10 megawatt scale. And the idea is once we show that this works, then we can expand that to other things. There is also a 50 megawatt SCO2 plant in LaPorte, Texas. This uses that oxy combustion cycle. So here they're using natural gas, they're putting natural gas in, but they're capturing any CO2 into the CO2 cycle, and they're releasing no CO2. So again, here's another site. They can give you a little plant tour. So if you go to here, you can click through and you can see the plant. If you go to this site, you can see the details of the supercritical CO2 step facility. So any questions on that for right now?
So would you say that the biggest kind of technological hurdles to get to this point have been the advanced materials, and like what has been improved in the last decade or so to get to this point where you can kind of demonstrate these projects?
Yeah, exactly. So advanced manufacturing techniques. So these compact heat exchangers, those are critical. Otherwise, you would have to have pretty massive heat exchangers if you did a shell and tube type technology. So the fact that we can take plates, we can etch them, diffusion bond them together, that allows us to create these small passages for these compact heat exchangers. The fact that we have better machining capability, we can get higher tolerances for these smaller machines is better. And then the advanced materials, looking at these nickel cobalt alloys, and the fact that the systems are smaller so we can utilize those without significant costs. So yeah, we kind of went through some of those things. So these wouldn't have been something that would be possible 100 years ago. We just didn't have the technologies available to make it efficient. They would have cost way too much money. They wouldn't have been efficient enough because the machining wasn't good and so forth. But now that we've moved a little bit further and we can use these advanced materials, go to these higher temperatures above 550 C, now they become much more efficient than the steam Rankine cycle. So it's kind of a paradigm shift with respect to that, led about by the fact that we can do this advanced manufacturing and so forth.
Do it.
You don't have to. You can run it at lower, but your efficiency goes down. It drops quite a bit. So for these applications where you're doing heat recovery, you're more like a typical Brayton cycle. So you're like 20% efficiency or something like that. You're still getting some back out where we were just throwing the heat from like these natural gas compressors out. Now we can make use of that electricity, but it's at a lower efficiency. So it's at like 20% efficient just because it's a lower temperature.
Do have a couple questions online.
Right.
First from Raj asks, is controls for supercritical CO2 cycle more complex than conventional steam Rankine cycle? Also, do you think that since the supercritical CO2 cycle is a closed loop system, any fault in any of the components would have a cascading effect and become difficult to restore?
So the first one is no. So they're not as complex. So you saw the picture between the Rankine cycle and the CO2 cycle. And you can see the complexity difference between the, oops. And you can see that, that's the one I want. You can see the complexity difference between the CO2 cycle and the Rankine cycle here. And so you have to monitor temperatures, you have open feed water heaters, you're probably going to have about 8 of these in a plant. And so you have all kinds of pipes, you have to monitor all these temperatures. Each one of these has a pump that pumps it to the next stage and so forth. So you have a lot more components to deal with. Here you have very few components. So these are all passive. This is just a heat exchanger. There's not much that can go wrong with that. This is a heat exchanger, that's a heat exchanger. You have the main compressor and the turbine. So you essentially have 2 different components. So they're quite a bit simpler to deal with. And the fact that it's a closed system, that doesn't really hurt you either. So all that means is that you're recycling this gas. So this gas is coming out of the turbine and you're putting it back into the cycle. And so it actually makes it more stable. So you're not associated with fluctuations of air temperature or anything. It's more stable in that particular case that you're running a closed cycle.
Sorry, one more question for now. It sounds like there are a few operating supercritical CO2 plants. What is the barrier to large scale adoption? Is it just time?
It's time and proof of principle. So the power industry is very conservative. So they like to move very slowly. They like to prove out that it's going to work. So typically when they build a plant, they want that plant to last 30 years. They want to have somebody say, okay, here's one that's operating at lower power. All we have to do is scale this up and we're good to go. So they're very risk averse. So that's a big hurdle in getting these things into the mainstream is you have to prove out the technology. But how do you prove out the technology without putting them on something? So there's this chicken and egg thing that we're fighting a little bit. But there are some demonstrations. And that's kind of why the Department of Energy stepped in and said, okay, we got to do a demonstration at a realistic level of 10 megawatts, show that these systems work. And then once people see how they work, then they can think about adopting them to their application. But before that happens, people are very wary, right? All right. No other questions on that? So now I wanted to...
As far as like the context of these systems go, do you think that lends itself better to microgrids? Because I know it's kind of an research topic is getting power that traditionally doesn't have it. Do you think that I guess the more complicated machine practices, like would that lend itself to those smaller communities, or would the complexity of the components itself kind of negate it?
Yeah, good question. Definitely, definitely. So there's a lot of work looking at these micro reactors, so looking at small nuclear reactors and so forth. And if you have this small nuclear reactor, but you have to have this huge steam Rankine cycle, it doesn't make a lot of sense, right? So it'd be much better if I have this micro reactor and I have this small turbine CO2 system. So a lot of these new technologies that are coming along, like Westinghouse with their eVinci reactor, and yeah, pick your favorite micro reactor. They're all keeping a very close eye on these supercritical CO2 cycles because they think that these marry up very nicely to those advanced reactors. And there you can have a distributed power system with a micro reactor and a supercritical CO2 cycle. Good question. All right. Okay, so I wanted to loop back a little bit to one of our first slides. And so we looked a little bit at the supercritical CO2 cycle, but another big part of energy utilization is the storage. And I know you guys have seen a bunch of different lectures on storage as part of this series going forward, but I wanted to talk a little bit about thermal energy storage going forward. So I think you've seen some stuff on batteries and so forth, but to make effective use of the energy that we produce, we have to be able to store it, especially as we add renewables onto the grid and so forth. And we've come up, as a society, we've come to a point where we expect this energy now. So I want to come in the room, flip on the switch, I want it to come on. Or I want to turn on my air conditioning right when I get home so that I can cool myself down. And so we're very dependent upon having energy at a specific time. And part of utilization is figuring out how to store that energy and use it effectively when we need it. So I don't know if anybody showed this in your other lectures, but This is the iconic duck curve. So this essentially just says that as we start to add renewables, we have to curtail some of the power generation that we have, because we have a lot of electrical energy generated from PV and stuff at times between, say, 10 a.m. and 4 p.m. But we don't necessarily need that energy at that particular time. So what we need it at this time, when everybody goes home and kicks on their air conditioning, we need a lot of power, and that's when the PV and wind starts to die down. So there's this system that looks like this, and as we add more renewables, then we have to curtail more power in this region, and we have to still meet these peak demands associated with it. And so this leads to energy storage a little bit. If you want to know more about the duck curve, you can go to these slides. This is a little video that was put on by the Department of Energy. It's pretty good. It goes through on how to do that. But there's many different types of energy storage. Essentially what we're doing is we're doing some of this arbitrage. So the cost of electricity can be expensive at some times and cheap at others. And there's also different time scales associated with the energy or storage. They could happen very quickly, where we have to do frequency regulation. They could be over seasonal type things. They could be daily. So there's a bunch of different needs for energy storage. And then you have a bunch of different technologies. So here I show some where you have batteries, we have compressed air. I think somebody talked about pumped hydro, you have flywheels, and all of these different energy systems come about at different power ratings and discharge time. So you have to pick your energy storage system depending on what the need is associated with it. I'm going to skip this slide. So there's several different kinds. So you have physical systems where you have pumped hydro, and I think somebody came and talked about that. Compressed air storage, I'll talk a little bit about that. Flywheels. Then you have thermal energy storage, electrochemistry, electricity. These are batteries. And then you have chemical. This could be like hydrogen or something like that. I think people have talked about these and talked a little bit about these. So I'm going to focus more on the thermal energy storage side. So first, let me talk a little bit about the first one, the physical. So there has been some designs looking at compressed air storage. So it turns out that we can take a compressor, and if we're in a certain spot, we can look at a deep salt cavern. We can run a compressor with energy that's going to be curtailed, and I can pump that into the air, and I can compress that into a big salt dome. And then when I want this out, I can bring it up and I can spin a turbine. So I have high compressed gas down here, and I can spin a turbine so I can get some energy out in that particular way. So that's a way to store energy. One of the problems with that is that it's very locational dependent. So I typically have to be by a big salt dome, otherwise it doesn't make sense. There has been some advances. Some people are looking at storing air in cryogenic tanks. So actually turning air into liquid, and then you can store it at a much higher density, and then you can eject it. There's a problem with that. The efficiency is not great because you have to compress to very high pressures to get to the liquid state. But there are people that are looking at this. And then this one was in the news lately. It's actually tied to the university, but and this also makes use of the supercritical CO2 cycle. So there's been some concepts that you could take supercritical CO2 and you could store that. So you take CO2 in a huge dome. So this is essentially a big balloon. And then you can take that, go through a compressor, it gets hot, you store it at the heat in this thermal energy storage system, and then you compress the CO2 to a liquid state. You store this as a liquid. And then when you want to discharge that, you take the CO2 out of here, goes through the thermal energy storage into the turbine, spins the turbine, and so forth. So this is a way to store it without any release of the CO2. We'll see how the economics work out and the efficiencies. They claim pretty high efficiencies. I don't think they can reach exactly what they're claiming. I think you could maybe get 30% round trip efficiency with this system. But it's another idea of energy storage. And then I wanted to talk a little bit about thermal. So there's different ways we can do thermal energy storage. One is sensible. So this is just the change in the temperature. So if I heat up a rock and then I can store that energy in the rock for a certain period of time and then I can get it out. We can also do a phase change. So I can change a phase. So I can take some material like a salt and I can go from a solid to a liquid. And there's a lot of energy associated with this phase change. And then there's thermochemical. I'm not going to talk too much about this. So this is what salt looks like. So this is, there's a bunch of different kinds, but this is actually a nitrate salt. So this is a sodium nitrate. It's very similar to the salt that's on your table or the salt that they throw on the roads to melt ice. And so it's in a solid form. Turns out that I can heat this and I can melt it, and then it turns into this clear liquid, and I can pump it just like water. So I can pump this around, but it's at atmospheric pressure. So this is liquid at atmospheric pressure at about 500 degrees C. So it's at high temperatures, but it's a liquid and I can move it around like a water. And so I can make use of this in a bunch of different energy situations. So one example that they're using this right now is CSP, or this concentrated solar. Again, this is a mirror field. This is your central receiver. You're shining all this light up there, heating it up, and I can pump this molten salt up into this thing, heat it up, and then I can store the hot salt in one of these tanks, and I can store cold salt in the other one of these tanks, and I can put my heat engine between this hot reservoir and cold reservoir, so that if clouds come over or something like that, I'm not disrupted with respect to my energy, and I can store this. I can actually store enough energy to go all over the night too. So now I can use solar energy and I can hit that peak of the duck curve by using the storage of this molten salt. There's a company called TerraPower that's working on a nuclear reactor. This is a sodium-cooled nuclear reactor, but they're integrating this molten salt storage along with it. This is actually Bill Gates started this company, and it was part of Intellectual Ventures, which he came up with. And it's a sodium reactor, but it's linked to this thermal energy storage with this molten salt. So one of the issues with nuclear power is you want to produce nuclear power all the time. And sometimes the price of nuclear power or the price of electricity goes negative. And if that happens, the company's losing money. So now with the fact that you can store this energy, now you don't have to sell it at a negative price. You can store it, and then you can produce more power when you need it. So integrating these thermal storage systems in with these different reactor concepts is beneficial. I'm not going to show this video, but this is one that we're working with Google and this company called Malta. It was funded by Bill Gates. So this is in one of Bill Gates' news notes. This is actually me in one of our labs across the street. So if you want, you can go to these slides and watch this little video that talks a little bit about some molten salt research we're doing on campus. One of these concepts that we looked at is storing thermal energy to create electricity. This seems a little crazy when you first look at it because you're taking high quality electrical energy, you're putting into thermal energy, and then when you want to back out, you got to go from thermal energy back to electrical energy. But with the cost of power and the storage issues, it might make some sense, and we can get pretty good round trip efficiencies. So there was a company that was started by Google. So this was a venture that was split off of Google. They were looking at trying to shear up their data centers and be able to have power at their data centers that was produced by green power. So say I take PV and I can put the PV or wind into this system. It's a fairly green electricity. I can heat up the salt, and then I can produce energy when I need it. And so I have some storage associated with that. So this works on a system where it's essentially just a heat engine. So we run in this particular system where we use a hot molten salt on the hot side, and then we use a refrigerant on the low temperature side. And so we're running at a low temperature and a high temperature. We saw from the Carnot cycle that we want to drive this as low as possible, this as high as possible. That gives us our highest efficiency. So by putting our heat engine inside of this, then we get pretty high efficiency, and we can get round trip efficiencies of about 50%. This is just a conceptual picture of some tests of this particular storage system that are starting to develop. So there's some work at Southwest Research Institute. This is an idea or conceptual idea of using this on an island-based system where if your power goes out, you need backup power, and you could do a system like this. And where they think that they fit with respect to this is up near the pumped hydro and this compressed air storage. So it's longer term, higher power, longer duration. So it doesn't really compete with the batteries that are more in this area. It's more longer term, larger scale energy. There's another concept that we looked at with phase change material. So the idea here is that you'd take a system and you'd fill this with a molten salt, and then you could melt that molten salt and make use of the latent heat of fusion in terms of energy storage. So this is a little experiment that we did with this molten salt storage out at one of our campuses just off of the main campus here. You can also do this in other, do thermal storage in other modes. So the idea here is you could take concrete, very cheap materials, and you could pump hot oil through here, heat up the concrete, and then store the energy that way. And there's been a lot of work with some of these coal plants that are located where next to these PV systems and wind systems are shutting down these old coal plants, and they have all the steam infrastructure there, they have the electrical infrastructure there. And so it turns out that it's very easy to take that coal plant that they shut down and put thermal energy storage in there and feed that with your solar power or your wind power. And then when you lose your solar power, wind power, then you can pull the energy from there. And you make use of their steam turbines and so forth that are already in these coal plants. So there's many people that are looking at this. One is Westinghouse. They have this design where they're doing basically the same thing. So they have these buildings here, which would just be large concrete buildings that have hot oil going through them. And then they have a water tank here that they can essentially freeze. And then they're running a supercritical CO2 heat pump that pumps the heat from the water into here, and then when they discharge, they take the heat from here and they run a thermal engine between it. And they're making use of the supercritical CO2 cycle also. So the idea would be something like this. So you have the pumped thermal energy storage, where you have a supercritical CO2 heat pump that's putting heat from this into the concrete. So it heats up oil, puts the heat in here. That pulls heat from the water tank and actually freezes this. And then the next stage is you have frozen here. These are charged. So this is hot. Now I can run my thermal engine between the two. So now I can start discharging. I have cold reservoir here, hot reservoir here. I can run this essentially backwards, and I can pull heat out. So these systems are being looked at, and they're actually being built. So there's one that's Westinghouse is doing I forgot what size it was. I think it's back on this slide. A 2 gigawatt hour pump system in Bulgaria. So they're currently working on this there. And then, oops, sorry. And this is just what I mentioned before. So you can take these salt systems, you can look at the conversion of a coal fire power plant, and you can put the systems in. So we're working with companies like Siemens and Shell Oil to see how these types of systems would work. So I think I'll stop there. I think we're at time and open it up for any quick questions. Questions?
Curious why, where
So it's fairly,
I think that um, the cost of
yeah, and it is. It's moving forward. So these, like the supercritical CO2 cycle, I mean, we started working on this like 10 years ago. So it's coming up to speed, and we're doing this demonstration this year at Southwest Research Institute. They have the plant at LaPorte. So it's starting to get integrated into the system. These thermal energy storage systems, right now we're working with Siemens. We're actually trying to put one on campus where we have a molten salt thermal storage system. So they are starting to be used. Again, it's hard to get the energy people moving forward, get them thinking a little bit. And also a lot of these, like our current plants here, the lifetime is 30, 35 years, 40 years. So you have these infrastructures that have just been built. Now you want to change that quickly. So I mean, it's hard to change that. So you have to kind of wait for the next iteration and say, okay, the next plant we build, we're going to incorporate these supercritical CO2 systems because we already put this ranking system in there. We're not going to change that right now because that'd be too expensive. But they are starting to be integrated. It's just a slow process to integrate them.
We got a few questions online here. Maybe I'll kind of do rapid fire. There's a few from Raj here. One is, do you think, and I think you kind of already addressed this, do you think we have to consider the round trip efficiency of different storage technologies from charge to discharge cycle and megawatt hour storage per unit of footprint area?
Definitely, right. Yeah, so for any of these storage systems, that's one of the first things you have to look at. What's the round trip efficiency? So we're not getting free energy by storing it, right? Any storage system is costing us energy. So you never get 100% energy out. Even a battery, you'll maybe get 85, 90% power out, but you're losing a portion of your power. So you have to look at that. So you have to look at the cost, and you have to look at the global costs associated with that. So with a battery, I got to mine lithium. I got to pay for the lithium. So you have to look at the entire life cycle associated with that too. What does it take to store that energy, and how much energy do I have to put in to store that? And then I'm not getting it all back. So certainly storage is important, but we have to consider the round trip efficiency, the scale of which we're doing it, and then the whole life cycle of all these different materials that go into the storage mechanism too. So that's one advantage of these molten salt systems is they don't really degrade. So you have this salt that they put on the roads and so forth that stays around. So it doesn't deplete. So you can have a large lifetime with very little change in your storage capacity. So I can run that for 30 years without any degradation with respect to the amount of energy that I get out. Yeah, my round trip efficiency is only 50%, but it's 50% over the life of the plant. Whereas if I have a lithium battery system, I might start off at 85% round trip efficiency, but that drops off over time. And now in 15 years, I got to replace that and I have to do something with it. So I got to recycle that and so forth. So you got to look at cradle to grave with these cycles, how much energy you're storing, round trip efficiency, all that, and it's important. And then there may be situations where you want to do industrial processes. In industrial process, maybe I want the heat. So there you might want to do some kind of thermal energy system. So like on a campus like ours, most of the energy that we use is in heating and cooling buildings. The electrical power storage doesn't do us a whole lot of good. What we need is thermal energy storage. So there's a difference on what kind of storage you need too. I'm not saying that batteries are bad. There's a place for everything. You just have to look at those.
And that's actually, Jeff asked, does UW need a thermal energy storage system? So why would you say a thermal storage would help with our heating and cooling?
Yeah, so all the buildings are linked together by a central plant, and they send steam to the buildings to heat them. And then they also send chilled water, and the chillers are run with steam. So mostly, they do have some electric chillers associated with them. But you have to send that heat around the campus. And so you don't want to take electrical energy and turn that back into thermal energy and push it, because then you've just taken a hit on how you generated that electrical energy. So you'd be better off storing it as heat and then moving it around.
And this might be difficult to answer. Do you know the estimated payback of some of these different storage technologies and the ease of retrofit to existing systems?
I don't know the numbers off the top of my head, and it's going to depend on the particular plant and the location, where you are, and so forth. But I can say that there are people interested in it, and there are people doing it. So, like I said, we're working with Siemens, we're working with Shell. There's these big companies that think that this is profitable, right? So they are actually doing this. There's a electrical company that is looking. This is in South Africa, but they're taking one of these coal plants and they're putting thermal energy storage because they have a bunch of PV and wind around it, and they think it's economical, and they're putting lots of money into it to test these different components and so forth. So I do think there is benefit associated with it, and I think that it will, because there is economic benefit, it will happen soon.
And final question, will the growing maturity of hydrogen applications make it more economical?
Hydrogen is great. So that's another storage mechanism. I think you can make use of all kinds of storage mechanisms. There you're taking maybe a nuclear power plant, you're creating heat, and you're doing electrolysis, making hydrogen. There's issues with it. How do you store it? How do you transport it? So there's a lot of issues around hydrogen. We don't have time to get into hydrogen storage capabilities, but I wouldn't say it's a bad idea. You can store it as ammonia or something like that, but then ammonia is more valuable as a fertilizer than it is a fuel. So there's all kinds of issues with some of these other things, but hydrogen is certainly an interesting storage mechanism, and you can store it for long periods. So there you can store it for a seasonal, right, which is a big thing.
Any final questions here in the room? All right, thank
All
you
right.
so much.
Yep.
And we'll see you all here next fall for the next Sustainable Energy Seminar Series.